Hello everyone, my name is Jingcheng Li. Today I'm gonna talk about our work POF Proof Following for Vehicle Platoons. At the very beginning, I'd like to introduce all the contributors in this work. First, Ziqi Xu and I are both PhD students at the University of Arizona. Then Yanjun Pan is an assistant professor at the University of Arkansas. Then both Dr. Lucas Lazos and Ming Li are my PhD advisors, and then Nirnimesh Ghosh is an assistant professor at the University of Nebraska-Lincoln. To begin with, the broad theme of my talk today is verification of physical property in cyber-physical systems. In particular, we focus on the security and safety of connected and autonomous vehicles. Our idea was motivated by the emerging of intelligent transportation systems, especially some connected vehicle technologies that allow vehicles can change messages such as traffic information, velocity between them. So this can improve the safety of the traffic and also the fuel efficiency. But on the other hand, this opened the door to a wealth of new attack, which I'm gonna discuss in this talk. A prime application of connected vehicle technology is the vehicle platoon, where vehicles are allowed to driving cooperatively, such as using a cooperative adaptive cruise control. Let's see an example with three vehicle platoon here. The distance between vehicles is dref. So by using the cooperative driving, the dref could be decreased to 0.3 seconds, which is 8 meters when their velocity is 60 miles per hour. Then this is about 10 times reduction from 3-second rule if drivers are driving manually. Another important property of Platoon is that their formation should be dynamic, meaning that if we're considering a two-vehicle platoon, the verifier should be able to accept new candidates to join the platoon when a benign candidate sends a request information to him. So once the candidate is admitted, he can inject his own messages to the whole system and then impact the cooperative adaptive cruise control. So establishing trust among all vehicles in the platoon is crucial in the platoon application. Next, let's see an example of verifying the identity of the candidate. So here we assume the identity of the verifier is known to the candidate, so the candidate can sign the encrypted joining message attached by his signature and certification to the verifier. Then the verifier can verify the candidate's digital identity. But here's a problem that how does the verifier know that the candidate is really platooning? Because there's no way to bind the candidate's digital identity with its physical location. If so, this opens some opportunities for the adversary who is trying to join the platoon without really following. We can see from the figure that adversary can send messages to the verifier through an infrastructure, or just sit at the roadside, or follow the platoon following far away from the platoon. So all the messages from the adversary could be accepted because he's holding a valid credential. If so, this adversary can control different platoon at the same time, but without following any one of them. So it is clear to see that the crypto is not sufficient to verify physical properties like location, time, speed, and so on. So we may need some physical world security methods. To solve this problem in Platoon application, we propose the concept of proof of following. The idea is given the route of V and C, the distance between two vehicles should be bounded by dref for any time instance during the route. So it provides a physical access control that only platoon members or only the candidate can prove his following to the verifier can participate in the coordinate platooning actions. So the POF property bears similarity with distance bounding, which is also a physical authentication mechanism, where the verifier assumes that the prover is in a close distance bound. However, some well-known distance bounding protocols require custom hardware and special physical layer to to get the high accurate distance measurement. So it will be good to think a simple method that can achieve the same goal. Our method our method was inspired by a simple game called I Spy with My Little Eye. The main idea here is that two entities traveling together should observe the same environment. They can use different modality here, such as visions, sounds, or ambient radio signal, depends on the availability. But the main important thing here is that the chosen modality should be dynamic in both spatial and time domain, meaning that the environment should change during driving, and also the marine opportunity changes over time. So in our paper, we choose RF modality. In particular, is the large-scale fitting. The hypothesis here is that when two vehicles driving closely, they can measure similar large-scale fitting from the same LTE tower. The reason we use large-scale RSS is that the theory tells us the correlation of two RSS sequence decrease according to an exponential model. As we can see from the figure, the y-axis here is the correlation of the RSSV and the RSSC, and x here is the distance between two vehicles and which is normalized by the decorrelation distance. The decorrelation distance is dependent on the environment and is typically equal to 50 meters for the highway environment. On the other hand, the temporal correlation decreases with time, and the RF signal could be measured using existing receivers, so we don't need extra hardware. Here, let me introduce a simplified POF protocol here. The candidate sends a request to the verifier, and the verifier verifies its digital identity, and then send a synchronization message back to the candidate to indicate when he can start collecting the RSS. And after collecting the RSS, the candidate sends his measurements back to the verifier, and the verifier computes the correlation of two datasets, and then decide whether accept or reject the candidate. So the POF verification test could be done through the following steps. Given the RSS value gamma C and gamma V, we partition the RSS set to k subsets of set n, and then we compute the endpoint moving average of each subset, and we compute the correlation of each subset pair and then compare it with the threshold tau. So if the k subset pair's correlation is higher than the threshold tau, we say rho k larger than tau, we say the candidate passed the single test. So to improve the security, we use multitest here. If the candidate can pass a portion of alpha of k, then the verifier can accept the candidate. Next, we did some experiment to evaluate the correctness and security of our protocol. We used different setup in different environments. So first, we used two manually operated vehicles with cruise control in freeway and urban environments while they were driving at 30 miles per hour and 40 miles per hour respectively. And in the highway environment, the verifier was on cruise control while the candidate was on adaptive cruise control. And their velocity was 55 to 60 miles per hour. At the bottom left are the hardwires we were using during the experiment. We use a laptop to control all the hardwire and use a USRP to sample the ambient RF signal, and then use a GPS receiver to receive GPS information to calculate the distance between two vehicles. And also we have a power supply. So here are the experimental results from the Freeway experiment. So to make our protocol work, we need to tune all the parameters over here. So on the left shows the correlation of two RSS sequences against the distance between two vehicles when we're considering different n. So as we expected, when the distance between two vehicles is smaller than dref, the correlation of two RSS set is high, but when the distance is large, the correlation of RSS set is low. The red figure over here showing the correlation of RSS set against distance between vehicles when we consider different moving average window set m. So larger m meaning smoother of the received signal, so it gave us higher correlation. But as we can see from the figure, after a certain value, this gain is diminishing. So from our experience, we suggest n equal to 400 and m equal to 20 are enough to use. So after turning all the parameters, we go to the results from the highway experiment. Here, the verifier was driving at 6 miles per hour and the candidate was following 53.4 meters behind on average. And the left figure here showing the passing rate of the candidate and the passing rate of the pre-recording attacker who's trying to record follow the same route ahead of time. So we can see with the increase of k, the passing rate of the candidate raised to 1, while the passing rate of the adversary go down to 0. The same thing happened on the right figure, when we can see that the passing rate of the candidate goes to 1 also, and the passing rate of the following of our adversary, who is following 200 meters behind, go down to 1 after k larger than 5. And we can observe almost similar results in the urban environment. In this experiment, the verifier was drive at 40 miles per hour, and the candidate was follow 11 meters behind on average. And we can see that the passing rate of the pre-recording attacker goes down to 0 if k is large enough, and the passing rate of the candidate was 1. And for the following of our adversary who's following 100 meters behind, the passing rate of this kind of adversary goes down to 0 after k larger than 11, while the passing rate of the candidates is 1. So far, we already showed that the following of our adversary or the pre-recording adversary could be defeated by our protocol efficiently. But there is a special case that the man-in-the-middle attack can break our protocol when the verifier is unknown to the candidate. And we introduced this how the attacker can achieve his goal in our paper, and we also gave a solution of this adversary by adding a delayed commitment to the protocol. And I will skip this part because of the time limit, and all of those are included in our paper. So as I introduced, our RSS-based POF protocol can determine whether a candidate is in the surrounding of the verifier, but it is not allowed the verifier to verify the relative order of the candidate and the verifier and the driving lane of the candidate. These two questions are solved in our new project. At last, let me summarize our main contributions. We developed a POF protocol which enables the candidate vehicle probe to verify that it is following. And then we exploit the large-scale fading property as a new modality. And then we demonstrated the security of our POF protocol against a different type of adversary. And at last, we experimentally evaluated the performance of and security of our protocol in different environments.